Welcome. Today we're talking about gas behavior. This is the gas laws, chapter 12 in our general chemistry course. The last chapter we talked about exothermic and endothermic reactions and how to measure enthalpy or heat changes, the heat content of a reaction. This chapter we're going to talk about the energy and temperature as they relate to the behavior of gases. So we're going to be talking about gas behavior. We've talked about this previously, but we're going to get a little deeper into it and talk about some of the gas laws that pertain. Why does a hot air balloon go up? Well, it rises when the air inside is heated. What about helium balloons? They rise because the helium is lighter than air. What happens when they lose the helium? Well, they sag, they collapse. So how does kinetic theory explain why a loss of helium in a balloon causes it to sag and collapse? Well, it's fairly simple. When the helium particles leave, there's fewer of them, which causes fewer collisions, which creates less pressure. So we're going to review kinetic theory. We already saw this back in chapter 10. But here are the basic assumptions that pertain to the gases when we talk about kinetic theory as it pertains to gases. First, the particles are very, very tiny and far apart, and therefore there are very little interactive forces. Essentially, we consider them to be negligible. These particles are in rapid, random motion, and they have perfectly elastic collisions, which means they don't lose any of their energy in their collisions. And the average kinetic energy is directly proportional to temperature. Now, which one of these 5 assumptions explains compressibility? That's the ability of gases to push down into a smaller volume. So here's a great example. If you have a syringe, you can press it and it will collapse if it's full of air. It will not collapse if it's full of water or a solid like sand. Well, it's the relatively large distances between gas particles that allows for compressibility, because that means there's lots of empty space, and so we can squeeze those particles into a smaller space and they don't push back. But we don't have that same flexibility when it comes to water molecules or solids. They're close enough together that we can't push them closer. This compressibility can be used to absorb energy, such as a collision. So here is a classic example of a collision and an airbag. As you can see, as this airbag inflates, the compressibility inside that airbag keeps the crash dummy, and hopefully you, if you're in that crash, from being wiped out. The compressibility of air also explains why shocks work, at least some kinds of shocks. And so as they travel up and down, they press against an air chamber and it absorbs the energy of the collision. Okay, which assumption explains why gases expand? Gas particles, remember, we assume that they have no attractive or repulsive forces between them. So they're free to move inside their containers, and they expand until they take both the shape and the volume of their container, no matter how big or how weirdly shaped. Okay, which assumption explains why gases have pressure? Well, the rapidly random moving particles collide, and those collisions are perfectly elastic. So the kinetic energy is transferred but not lost. And so the sum total of those collisions creates pressure. So there are 4 variables we use to describe a gas. We talk about the pressure. We generally measure that in kilopascals, sometimes atmospheres. Volume, which we measure in liters. Temperature, which we measure in Kelvin. And the amount of gas, which we measure in moles. So these are the factors that will affect gas pressure. All right, so let's consider something like a soccer ball. What makes the pressure inside the ball? What factors affect it? Well, obviously the amount of gas that we have inside the soccer ball. The temperature of that gas. So you can have the same amount, but on a warmer day, the ball will be more firm, there'll be more pressure because, again, the average kinetic energy is directly proportional to the temperature. It also depends on the volume inside the ball, right? If you have the same amount of gas in a soccer ball as in a basketball, it will be more pressure inside the smaller volume, but less pressure inside the larger volume, like the basketball. How does increasing the amount of gas affect pressure? Well, that's pretty simple. That's what we use a pump for, right? We take a ball, we put the pump in, we pump it up, we add more gas. We do the same thing with our tires, whether it's our bicycle tires or our car tires, we add more gas to increase the pressure. More particles equals more collisions equal more pressure. So as long as the temperature doesn't change, it's fairly intuitive. If we double the amount of gas particles, we'll double the pressure. If we triple the particles, we triple the pressure. So we can do this until we exceed the strength of our container. If we get more gas in there than the container will hold, the container will burst. But yeah, letting the air out reduces the tire pressure because we reduce the amount of gas in the container. So if we start with something here that has 200 kilopascals and we let the gas out, we let half the gas out, we are going to have half the pressure. So it's just the reverse of adding particles. Removing particles decreases pressure. Having the number of particles, cuts the pressure in half. When a sealed container of gas is opened, gas moves from high pressure to lower. So this is a higher pressure inside here. When we open the valve, the gas is going to go from high pressure to low pressure. And what is a common use for this? Well, a spray can, a paint spray can or something like that, a WD-40 can. The gas inside, which is used as the propellant, wants to go from the higher pressure inside the can to a lower pressure outside. And that propellant forces the product, whatever it may be, whipped cream, hairspray, paint, WD-40, and pushes it out. How does decreasing the volume of gas affect pressure? Well, if we reduce the volume by half, we double the pressure. Why? It's fairly simple if you think about it, right? We've taken all those particles and we've reduced the amount of space they have to move. So they're going to double the collisions than they would have in the larger space. You double the average collisions, you double the average pressure. So if we cut the container volume in half, the pressure of the gas is doubled. What effect would doubling the volume of an enclosed gas container? So if we half the volume, it doubles the pressure, but if we expand the volume, what's going to happen? Pressure is going to drop, right? Because there are going to be fewer collisions. How does increasing the temperature of gas, the temperature now, affect pressure? Well, we know that the speed and the overall, the average kinetic energy of gas particles increases as the particles absorb thermal energy. And so we know that if we double the Kelvin temperature, we'll double the average kinetic energy, and that will, of course, double the pressure. So far, all this is a review. Oh, yeah, and if the temperature gets too high, and again it exceeds the ability of the container to hold it, it can explode. This is why if you throw an aerosol can, even an empty one, in a fire, for example, you get an explosion. Okay, that leads us to the next section, gas laws. Now these are going to give us some mathematical expressions that relate these various factors. The first one we're going to look at is Boyle's law. And this is the relationship between pressure and volume. Now, Boyle was a natural philosopher, a chemist, a physicist, an inventor. He was born in Ireland, and he is known for Boyle's law, which is that the volume of a gas varies inversely with pressure. So that means as one goes up, the other is going to go down. So as the volume goes up, the pressure will go down. As the volume goes down, the pressure will go up. So they will move in inverse proportion. The nice thing about that is if you multiply them together, it is a constant. So this is the mathematical expression of Boyle's law. The pressure in the first vessel times the volume of the first vessel is going to be equal to the pressure in the second vessel times the volume of the second vessel. So here, our volume is 1 and our pressure is 1. Well, here our volume is half, so our pressure is going to be double. And as you see, 1 times 1 is 1, or 2 times a half is still 1. So P1V1 equals P2V2. You can see this if in a Bell vacuum, if you decrease the pressure, you're going to see the potato chips expand into the decreased pressure. So you decrease the pressure, they'll expand. If you increase the pressure, they'll contract. So at a given temperature, the product of pressure and volume is always a constant. And we represent that with just this letter K. So pressure times volume is always constant. And since the pressure of one thing times its volume is going to be constant, so it is with the pressure of another thing times its volume. And since two things equal to the same thing are equal to each other, we get this expression here. P1V1 equals P2V2. All right, let's look at sample problem 12.1. A high-altitude balloon contains 30 liters of helium gas at this pressure. What is the volume when the balloon rises to an altitude where the pressure is only basically a quarter of that? Assume that the temperature remains constant. So here's our knowns and our unknowns. We know P1, V1. We know P2, but we don't know V2. So we know we're going to use Boyle's law here. We know 3 out of 4 of these things to calculate our fourth unknown. So we're just going to rearrange this to get V all by itself, V2 all by itself. So that gives us V1 times P1 over P2. We put those known values of those 3 things in there, 30, 103, 25, and we're going to get this volume. Now, does it make sense? Yes, a decrease in pressure must correspond to a proportional increase in volume. And all the units have canceled the way we expect it to, and we've expressed it with the correct number of sig figs. This takes us to Charles' law. Now, Charles' law is going to look at the relationship between temperature and volume. Remember, Boyle's law is pressure and volume. Now we're going to look at temperature and volume. Jacques Charles, French physicist, he was part of a scientific balloon flight and was one of 3 passengers in the very second balloon ever to lift off carrying human beings. This was in 1783. He became interested in gases after this. The balloon was filled with hydrogen, just like the Hindenburg was. Happily, it didn't light on fire. But what he noticed is that at constant pressure, as the temperature goes up, the volume will go up. Now notice this is different from the pressure-volume relationship, right? Pressure-volume, they go in different directions. But these both go in the same direction. Temperature goes up, volume goes up. Temperature goes down, volume goes down. So you can see this easily in demonstration. If you have a balloon, you put it in ice water, it's going to shrink, get smaller. But you put that same balloon without changing the amount of gas, you put it in hot water, it's going to absorb the thermal energy and it's going to expand. So again, we haven't changed the pressure. We still are under regular atmospheric pressure here. But what we see is that as the water decreases, the volume decreases. As the water increases, or the temperature, increases, the volume increases. So Charles's law is that the volume of a gas is directly proportional. Remember, Boyle, it's inversely proportional. But the volume of gas is directly proportional to its Kelvin temperature if we hold the pressure constant. So put a balloon over a candle, it expands as it absorbs thermal energy. And under the atmospheric pressure, it will get bigger. Mathematically, we can say this. We can say, since they are directly proportional, that if we divided one by the other, we get a constant. So V1 divided by T1 equals a constant. So it's the same as any other time we can take a V2 divided by T2, and that will equal the same constant, which gives us two things equal to the same thing or equal to each other. So V1 divided by T1 equals V2 divided by T2. So we can see this demonstrated here on a graph. As we increase the temperature, the volume is going to have a straight line increase. So it's a direct proportion. You double the temperature in Kelvin, for example, you double the volume. Now, one interesting thing that comes out from this is that because this is a straight line, now at a certain point, we just can't, the gas just, we can't get it any colder. Or when we do, it goes into a liquid. But if you extrapolated these lines down, just backwards, 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 a very interesting thing happens. They converge, all of these slopes converge at the same point. And that point is negative 273 degrees Kelvin, or 0 degrees Kelvin, or absolute zero. In fact, this was one of the experiments, and when people noticed this, they said, you know what? This seems to point to a time or a temperature at which our volume would be zero, at which we would have zero motion and therefore zero pressure. And even though this turns into a solid or liquid before this, we can extrapolate this back to absolute zero. So it was Kelvin who noticed this, and this developed the Kelvin scale based on this linear relationship between temperature and volume, Charles's law. So we can only measure that relationship over a limited range, but if we extrapolate or extend the lines down to zero volume, we get this lowest of all possible temperatures. So, as I mentioned, Lord Kelvin noticed this and realized that this was the lowest possible value. It wasn't just a very cold value, it was the lowest possible value. And this is where he establishes absolute temperature scale. And like any good scientist who discovered something, he got to name it, and he wanted to name it after the most interesting person he could think of, himself. All right, it takes us to sample problem number 2. A balloon inflated in a room at this temperature has this volume, 4 liters. The balloon is then heated to a temperature of 58 degrees. What is the new volume if the pressure remains constant? So what do we know? We know 3 out of 4 of our things, right? We know V1, T1, we know T2, we don't know V2. So we're going to use Charles's law. V1 divided by T1 equals V2 divided by T2 to calculate what we don't know, namely the volume of the balloon at this new temperature. So remember, anytime, this is key, anytime we use gas laws, we always express our temperatures in Kelvin. So the first thing we're going to do is convert these temperatures to Kelvin. Right? And the conversion is you take the degree and you add 273 to get Kelvin. So 24 plus 273, 58 degrees plus 273 gives us our degrees Kelvin. Now we rearrange the expression to isolate V2, put it on the side, so it's V1 times T2 over T1. We substitute what we know, solve for V2. So at this new temperature, so what, before it was 4 liters, at this new temperature, it's going to be 4.46 liters. Does that make sense? Sure. The volume should increase with an increase in temperature. We increase the temperature by by what, 34 degrees? And so we would expect a modest increase in volume, and this is exactly what we see. All right, that takes us to the third of the gas laws, Gay-Lussac's law, which relates temperature and pressure. Okay, so you see, we're just relating these relationships to each other. This time, we're going to consider the relationship between temperature and pressure. So, what Gay-Lussac noticed is that there's a direct relationship between the temperature and the pressure of a gas. If one increases, so does the other. So, if our volume is held constant, say in a fixed metal container or something, basically, if we juice the temperature, we juice the pressure. If we reduce the temperature, we reduce the pressure. And so that is another direct relationship, just like Charles's law. And so we can express this just mathematically. We can express this as, we know that P1 over T1 is going to be constant, which means it's going to be the same as some other pressure divided by its other temperature. And since these two things are equal to the same constant, they're equal to each other. So P1 over T1 equals P2 over T2. That takes us to sample problem 12.3. Okay, we have some gas in a used aerosol can, and the pressure is at standard, this is 1 atmosphere at this temperature. But if we throw the can on the fire, what's the pressure of the gas when its temperature reaches 900 degrees? And this will show us why it's dangerous to put aerosol cans in a fire. So what do we know? Well, we know P1, our initial pressure. We know our initial temperature. We know our final temperature. What we want to find out is what is the pressure at this second temperature. So we're going to use Gay-Lussac's law, P1 over T1 equals P2 over T2 to calculate our unknown. Remember, anytime we do temperature, we have to convert to Kelvin. It's just a given. You just have to lock that one away. You must convert your temperatures to Kelvin anytime you do a calculation involving gases with temperatures. So we convert Celsius to Kelvin by adding 273 to each of our temperatures. Then we rearrange the Gay-Lussac's law to solve for our unknown P2, plug in our knowns, do our calculation, and we get this. Now look at this, 415 kilopascals. Remember, we started at 100, so we quadrupled, right? We quadrupled the pressure. And that makes sense, right? We would expect an increase in temperature to produce an increase in pressure if the volume remains constant. And this is why you don't incinerate aerosol cans, because they can create massive pressures and explosions, resulting explosions. Okay, how do you remember all of these three different gas laws? Well, happily, there is a combined gas law. We can combine all three of these relationships, Boyle's law, Charles's law, and Gay-Lussac's law, into one combined gas law. So you don't have to remember three different separate things. You can remember one combined thing. So we take P1V1, which is equals P2V2, that's Boyle's law, and we combine it with P1 over T1, which equals P2 over T2, which is Charles's law, and then we combine it with V1 over T1 equals V2 over T2, which is Gay-Lussac's law, and we get this expression, P1V1 over T1 equals P2V2 over T2. So this is just, we're combining all of these relationships in one expression. And we're going to see how this gives us the ideal gas law here in just a second. But the first thing we want to see is that we can combine, instead of just any two, now we can combine all three relationships in a combined expression. And we can convert back to any of the other laws by holding one variable constant. So think about this. If T1 and T2 are constant, then they just disappear because it's going to be the same. So if these are both the exact same, then we go back to P1V1 equals P2V2, which is Boyle's law. If you hold pressure the same, then those basically they cancel out, and then we get V1 over T1 equals V2 over T2. Right? If we hold volume the same, then we get P1 over T1 equals P2 over T2. So by holding any one of these three variables constant, we can go back to the individual expressions. All right, the next sample problem, we have a volume of a gas-filled balloon. It's 30 liters at this temperature and this pressure. What volume will the balloon have at standard temperature and pressure? Okay. So standard temperature and pressure is what? Well, standard temperature is 101, and standard temperature is 273, and so we're going to convert these. So we're going to use now the combined gas law to calculate our unknown. So we know V1, we know T1, T2, P1, P2. We have to solve for V2. So we're just going to use, after we convert our temperatures to Kelvin, we're going to use the combined gas law. We're going to isolate our unknown variable V2, put all our other variables over here, and then we're just going to plug them in and do our calculation. So our final volume is 39.5 liters. That takes us to section 12.4, ideal gases. We need to go now to the ideal gas law. So we've talked about these three things: pressure, volume, and temperature. Remember, Boyle, he related pressure and volume. Charles related volume and temperature. And Gay-Lussac related pressure and temperature. And we can put all three of them together in the combined gas law. But there's a fourth variable that we haven't talked about yet, and that's the amount of gas in moles. And so, as you would expect, we can put all four variables together and we get a combined gas law known as the ideal gas law. And what we noticed also is that just like these other things, volume is directly proportional to the number of moles. If you have more gas, as the amount of gas goes up, the volume is going to go up. As the amount of gas goes down, the volume is going to go down. And so we're going to add that extra variable to our equation. So this is now it's P1V1 over N1T1 equals P2V2 over N2T2. Again, if any of these are held constant, so if we have the same amount of gas at the same temperature, then these bottom two variables drop away and we go back to simply Boyle's law. So anytime any of these are the same, they just drop out and it simplifies to one of the other laws. Something to note, temperature must always be in Kelvin, pressure must be in atmospheres, or torr, or pascals, or kilopascals, but whichever way you do it, it has to be the same for both. So if your atmospheres here, it's got to be atmospheres here. If it's kilopascals, so on. Volume, again, has to be consistent. It can be in milliliters or liters or cubic centimeters, but it has to be the same for both. And N is always going to be your number of moles. So this is our combined gas law, including our fourth variable, moles. And if we put all these things together, remember each one of these had a constant. Well, we can combine all the constants together into a combined constant, an ideal gas constant. And so we can say, just like P1V1 over N1T1, that's going to be a constant. And both of these are going to be equal to that same constant. Well, that constant we call R. And R is simply this. R is, if we're using liters and atmospheres and moles and Kelvin, then our constant is 0.821 liter atmospheres per Kelvin mole. So this, again, is the one thing you need to remember from all these other ones is PV equals nRT. And remember that P is pressure, volume, this is moles, this is our universal gas constant, and this is temperature in Kelvin. And under standard conditions, we can see, that's what's 1 atmosphere. Our volume of a mole, right, is 22.4 liters per mole. Standard temperature is 273. And we just do the math on that, and that gives us our constant. So this is called our universal gas constant, 0.0821 liter atmospheres per Kelvin mole. Probably worth remembering that. Okay, so again, that's how we derive it. We can convert back and forth from PV equals nRT to any of our other volumes. So for example, if we have PV equals nRT, that's going to be a constant, right? PV over NT equals R, which means that PV over any other NT is going to equal the same PV over NT. And if the temperature and the volume are constant, and the moles are constant, it reduces to Boyle's law. If pressure and moles are constant, which they frequently are, you get Charles's law. If your volume and moles are constant, you get Gay-Lussig's law. And we haven't talked about it yet, but you can actually get Avogadro's law as well. So just again, quick overview, the ideal gas law formula: pressure, volume, moles, gas constant, temperature, in what? Always Kelvin. Sample problem 5. Right, we have a steel cylinder with a volume of 20 liters filled with nitrogen gas, and to a final pressure of this at this temperature. How many moles does the cylinder contain? Now that sounds like a complex question, but then you go, wait, what do we have? I know P, I know V, I know T. What am I solving for? Moles, that's N. PV equals nRT. So this is our universal gas law to calculate our unknown. So first thing we're going to do, convert our temperature to Kelvin. We're going to rearrange the gas law to isolate N, put N by itself. We're going to plug in everything we know to find what we don't know, N. And as we're going to see, it's going to give us 160 moles. Does this result make sense? The gas is at a high pressure, but the volume is not large. That means that the number of moles must be compressed into that volume. So this large answer is reasonable, and we're confident because all of our units have canceled correctly. And this is why it's important to keep all your units here, especially the units for R, because R is going to have 4 units to cancel out 3 of the other 4 and leave you whatever you're looking for. So remember, yeah. Let's look at another sample problem, 12.6. An underground cavern contains this many liters of methane gas at this pressure and at this temperature. How many kilograms of CH4 does this natural gas deposit contain? Now, what they're asking for here is moles, right? We want kilograms, but we can get kilograms from our moles. So we can calculate the number of moles using the ideal gas law. Then we can convert moles to grams using the molar mass of methane, and then convert grams to kilograms. So that's the strategy. So don't get thrown off just because it's, remember, we can go to the mole or from the mole, and in this case we're going to go to the mole and then from the mole back to kilograms. So first thing we're going to do, we're going to convert our degrees Celsius to Kelvin. We're going to rearrange our ideal gas law to isolate N to find the number of moles. Okay, so remember that's going to be, here's our rearranged gas law. We're going to put our known quantities into the equation to find our unknown, making sure all of our units cancel. So in kilopascals, it's a slightly different constant. It's 8.31, but that will be given to you. There's different, you'll have one form or a couple forms of R to use, depending on whether you're using joules or kilopascals or atmospheres or whatever. All right, so that's going to give us the number of moles that we have. Then we're going to convert from moles. We're going to get our molar mass. So we know that when we add up all the H's, which are 4 grams each, and all the carbons, which are 12, we get Our molar mass is 16 grams per mole. So we're going to calculate, we just use that as our conversion factor. We start with moles, we're going to cancel moles, get to grams. Okay, that gives us grams, and then we convert that to kilograms by dividing it by 1,000, and oh, there we go. There's our final answer, 2.05 times 10 to the 4 kilograms. Does this make sense? Well, the volume and the pressure of the methane is very, very large. And so it's reasonable that the cavern contains a very large mass of gas. And we've calculated our units and canceled them correctly. So yeah, it makes sense. This takes us to the ideal gas law and kinetic theory. Remember, this equation, PV equals nRT, assumes that gases are ideal, that they follow the gas laws at all pressures and all temperatures. And what do we know about making these assumptions that everything's always ideal? We saw this in stoichiometry, right? Not everything goes to completion. Not every reaction gives you 100% product. We have all kinds of things that are less than ideal, and as you would assume, gases are the same. We do assume that gases are ideal, and some behave close to ideal, but some do not. So it assumes that kinetic theory is perfectly true, that gases take up no volume and have no attraction. But is that really the case? Right? That's in theory, but not in reality. No ideal gas exists. Every gas takes up some volume, and every gas has some, even if it's a very small, amount of attraction to one another, all these particles. But at many pressures and temperatures, real gases do behave very much like an ideal gas. And so that's why it's in some situations, it's okay to assume that the gas will behave like an ideal gas. But here is a classic counterexample, right? This is dry ice, which is solid carbon dioxide. How can we have solid carbon dioxide if it has no attraction to itself? Here's liquid nitrogen. And how can we have liquid nitrogen if it has no attraction? You couldn't have gases in liquid or solid form if they were truly ideal. So obviously they are departing from the ideal gas law. And if we plot this out, if this blue line here is the ideal gases, the ideal gas law, you can see that at certain pressures they depart from what's expected. And so in some cases they go lower than you'd expect, and then they go higher. So all real gases are going to depart in some areas from their expected behavior if they were an ideal gas. So our next section is gas molecules and how they mix and how they move. So this takes us to Avogadro's hypothesis, which we alluded to earlier in this chapter. We know that different gas particles have different sizes and different weights, right? We can calculate their different molecular weights according to the periodic table. So we know hydrogen is very light and going to be much smaller than, say, oxygen, which is smaller than chlorine. And so you can see here the relative sizes of some very common gas molecules. Here's water, here's methane, here's ammonia, so on. So these have different molecular weights, and as you can see from the relative sizes of their molecules, different molecular sizes. So people naturally assume that if you had a larger collection of molecules, well, that had to take up more space than smaller molecules, right? If you had 100, fat molecules like chlorine, that would take up more space than 100 hydrogen molecules that were much smaller, right? That makes sense. 100 bowling balls are going to take up more space than 100 ping pong balls. Right? That's just common sense. So scientists reacted in disbelief in 1811 when they heard Avogadro's hypothesis. And Avogadro, for whom our mole is named, right? That's Avogadro's number, 6.02 times 10 to the 23rd. He got that name not because he had anything to do with the mole, but because of this astonishing breakthrough when it came to gases. And to honor him for that, they named the mole, at least the number of calculating a mole, after him. But it was for this breakthrough in the area of gases that he is justly famous. And so here was his hypothesis, that equal volumes of all gases at the same temperature and pressure contain the same number of molecules. He said they all have the same number of molecules. Even if they're made up of bigger or smaller molecules, they all take up the same amount of space. Now, that seemed like he was suggesting that you could have two rooms of the exact same size, and they could be filled with the same number of objects, whether the objects were ping pong balls or basketballs, or something in the middle. Does that make sense? If you had a room full of basketballs, would it have the same number of balls as a room full of ping pong balls? Or a room full of tennis balls? Right? That seems absurd, right? You take a 5-gallon bucket of marbles, right, which are tiny, there are going to be more marbles in here than a 5-gallon bucket of tennis balls. But remember, gas particles are very, very, very far apart, with nothing but space in between them. So a collection of relatively large particles doesn't really require any more space than the same number of relatively small particles. They're all surrounded by empty space. Even if one molecule is 5 times bigger than the other molecule, they can still exert the same amount of pressure and take up the same amount of total volume. And we can demonstrate this now by experiment. And so that's why we say, and now it's become a commonplace, right? We say, oh yeah, a mole, that is Avogadro's number of gas particles, regardless of particle size, at standard temperature and pressure, takes up the exact same volume. We call this the molar volume of gases. And it was Avogadro who came up with this mind-bending idea. This also makes sense according to our kinetic theory, because if we have equal number of particles in equal volumes at equal temperatures, then they're going to have the same average kinetic energy and therefore the same pressure. And again, it's not going to matter on the size of the particles, okay? Because the particles are going to have the same energy, exert the same pressure regardless of their size. So whenever we have equal volumes of gases at equal temperature and equal pressure, the volumes should contain equal numbers of particles. As contrary to our macro experience as that seems, in the micro, that's the case. So let's determine the volume in liters occupied by this number of moles of gas at standard temperature and pressure. Okay, well, here's the number of moles. Here is, and what we're looking for. We're looking for the volume of this. Well, we know we can convert from moles to volume, right? We have a conversion factor, thanks to Avogadro. Any gas at standard temperature and pressure is going to be 22.4 liters per mole. We have this many moles. We're just going to multiply it by this conversion factor. Our moles are going to cancel. We're going to get liters. So this many moles gives us 4.52 liters. Does it make sense? Yeah. That's about a fifth of a mole. That's about a fifth of the molar volume of a gas. Okay, another problem. How many oxygen molecules are there in this many liters of oxygen at standard temperature and pressure? Well, what are we going to do? We're going to go from volume to moles, and then moles to molecules. Remember, when in doubt, go to mole island. Go through the mole. So we're starting with our volume. We're going to convert that using our molar volume of any gas, 22.4 liters per mole. And then we're going to, we know that there's Avogadro's number of molecules per mole. So we're going to stack all that together, convert from liters to moles, and then from moles to molecules per mole to give us a total number of molecules. 9.03 times 10 to the 22. Does this make sense? Yeah. This should contain about 1/7 of a mole, and that means 1/7 of an Avogadro's number of molecules, and that's what we get. All right, another sample problem. Determine the volume in liters occupied by this many grams of nitrogen gas. Well, what are we starting with? We're starting with a mass. What are we going to do? Go to the mole. Mass to mole, and then mole to volume. And we know those conversion factors, so we're simply going to apply them, right? We're going to say, okay, well, what's our molar mass of nitrogen? Okay, we have 2 N's at 14 apiece, and that's it. And we start with grams, so we go from grams to moles, and then moles to volume, and there we go, 11.2 liters. Does this make sense? Yeah, the mass of nitrogen corresponds to about 1/2 mole of N2, and 1/2 mole of N2 should be about half of 22. Boom, we're there. This takes us to Dalton's law. Dalton's law is that the total pressure of a mixture of gases is simply the sum of all the individual pressures. So if oxygen by itself exerts 0.4 atmospheres and nitrogen by itself exerts 0.6 atmospheres, when you combine them together, you'll have 1 atmosphere. So the total pressure is the sum of all the partial pressures. That's Dalton's law. So we look at the composition of air, and we find nitrogen, 78%, oxygen, just under 21%, carbon dioxide, 0.4%, and argon and others, less than 1%. And as you would expect, the partial pressure is going to be in exact proportion. If nitrogen is 78% of the volume, it's going to be 78% of the total partial pressure. Since our kilopascals is 101.3, that's exactly what each of these are. Each of these are it's volume percent of the total pressure. So again, just another way of saying the same thing. The pressure of a gas is equal to the sum of all of its components. So the total pressure is equal to all of the partial pressures added together. Another sample problem. So air contains all this stuff: oxygen, nitrogen, carbon dioxide, trace amounts of other gases. What's the partial pressure of oxygen at standard pressure if the partial pressure of nitrogen and so on are these other things respectively? Well, so they're saying we know these other partial pressures. What's the pressure of oxygen? So we know everything but oxygen here. We know the total. So basically, the total is oxygen plus all these others. So if we just subtract all these others from the total, that will give us our unknown oxygen. So we're going to take our total pressure, we're going to subtract all of our other partial pressures except for oxygen, and whatever's left over must be the partial pressure of oxygen, because the total pressure is the sum of all these other pressures, all the partials together. Does our result make sense? Yeah, it's got to be smaller than nitrogen because the total pressure is only just over 100. The other partial pressures are small, so yeah, this makes sense. Graham's law, or why does perfume circulate in the air law. Graham's law talks about diffusion. Diffusion is the tendency of molecules to move from areas of higher concentration to areas of lower concentration until you get a uniform concentration. So if I put dye in water, food dye in water, it's going to diffuse, it's going to mix as the water molecules move randomly. This is what kinetic theory would expect us to, would lead us to expect. And this diffusion is is very predictable, and it follows. And what we can see here is it's also going to be dependent upon temperature. So what you have here is you have a colder glass of water and a warmer glass of water. And look at the speed of diffusion in the warmer water. See, this is going kind of slowly, and then this in the warmer water is markedly faster. Okay, diffusion versus effusion. All right, diffusion is what we would already expect. You spray perfume in one corner, and pretty soon, over a period of time, it diffuses. It goes from being highly concentrated in one area of the room until it's in a uniform concentration throughout the room. Effusion is a different thing. It describes the diffusion of a gas through a tiny hole. So if you have an area of high pressure, like inside a balloon or inside a tire, and then you have a small hole or some sort of aperture, effusion is how fast that air will leak out or diffuse through the hole. So diffusion in general is when you don't have anything blocking it. Effusion is a particular kind of diffusion, but it's from an area of high pressure through a hole or some small aperture. It's easy to get them confused. So just think about if you had two different gases and you had a partition between them, and you remove the partition, then the gases would mix, right? They would diffuse. If you had gas only on one side, and then you had a pinhole, and then you just had a vacuum on the other side, then it would effuse through the hole. So diffuse is just mix. Effuse is everything has to go. It comes from an area of high concentration through a hole into an area of lower concentration. That's our terminology. Okay, well, Graham said, hey, there's laws that pertain to this. He noticed that the rate of diffusion is inversely proportional to the square root of the molar mass of the gas. What he noticed about diffusion also applies to effusion. It's going to be proportional to the square root of its mass, that as well. And so you get this mathematical expression, and this is from physics. This is the kinetic energy is 1/2 mv squared. The velocity is going to be the square root of the inverse of these. So here's the bottom line for Graham's law. Here's your takeaway. If two bodies have different masses, but they have the same kinetic energy, the lighter one has to move faster. And the lighter one is going to diffuse faster and effuse faster. Right, so we already know that particles of two different gases at the same temperature have the same average kinetic energy. Thus, the particle of low mass must move faster than the particle of high mass if they're both at the same temperature. If they're going to have the same average kinetic energy, that means the same average speed, which means that the one with less mass must be moving a tiny bit faster in order to have the same energy. If it's moving faster, the lighter gas should therefore diffuse and effuse faster, and that's what happens. So the rate of effusion, Graham's law of effusion, is that the rate of effusion is going to be inversely proportional to the square root of its mass. And you can use this to find the molar mass of gases. So for example, we have an unknown gas that diffuses 4 times faster than oxygen. So let's find its molar mass. Well, what this means is that the speed of gas A, the ratio of that, right, is 4 times faster. So that means we'll say that the velocity of A to B is 4. Well, that's going to be inversely proportional to the square root of the mass of B over A. And we know the mass of oxygen. Okay, we know its molar mass. And so we can put that in here, and then we can solve for the molar mass of this unknown gas. And in this case, it turns out that it must be 2.0 grams per mole. which means it must be hydrogen. So that's a Graham's law problem. That's the behavior of gases. Thank you for your time.